Hi, this is Dostojevsky. Class is Discrete Structures. We're up to section 3.4, the homework for section 3.4, equivalence relations and partitions. So we go through a lot of different relations and we show that they're either equivalence relations or they're not equivalence relations, and then we look at what partition that corresponds to. Okay, it's pretty quick. Okay, so a lot of it is reading. So we're up to number 1. These are the problems we're going to do. Which of the following describes equivalence relations? For those that are not equivalence relations, specify which of reflexive, symmetric, or transitive fail, and illustrate the failures with examples. L1 is parallel to L2 for straight lines in the plane L1 and L2 are the same or are parallel. So you got a lot of lines all over. Okay, and the question is, are two lines the same or parallel? This seems parallel. This seems the same. Okay, this seems parallel. Okay, so we want to know if that is a reflexive, symmetric, transitive. So let's go through it. Is every single line the same or parallel to itself? And the answer is yes. It is itself. It is itself. Every single line is parallel to itself or the same to itself. Is every single line symmetric to itself? And the answer is yes. If this line is parallel to this line, then this line is parallel to this line. If this line is parallel to this line, then this line is parallel to this line. So if one parallel is a symmetric relation, if one line is parallel to another, then the other is parallel to it. Transitive. If this line is parallel to this line, and this line is parallel to this line, does that mean that this line is parallel to this line? And the answer is yes, yes. Okay, so it is an equivalence relation. So that's very nice. Okay, B. Let's see what that is. L1 perpendicular to L2 for straight lines, if L1 and L2 are perpendicular. L1 perpendicular L2. So we have all those lines. Some of them are going to be perpendicular to each other. That means they meet at a 90-degree angle. So those two are perpendicular. This. Okay? We have to do it. So, again, we ask the same question. Is it reflexive, symmetric, transitive? It's not reflexive. A line is not perpendicular to itself. Okay? A line is not perpendicular to itself. Okay? It's itself. It's not perpendicular. Perpendicular means it meets at 90-degree angles. It is symmetric. If this line is perpendicular to that line, that means they meet in 4 90-degree angles. They both meet in 4 90-degree angles. The next one is a little bit more complicated, transitive. If this is perpendicular to this, and this, okay, all right, let's do this. Let's call this L1 is perpendicular to L2, and L2 is perpendicular to L3. What does that mean? Here's L3. L2 will meet L3 in 4 things. Is L1 perpendicular to L3? And the answer is no, they're parallel in fact. So it fails there. Okay, number C. P1 is related to P2 if P1 and P2 live in the same state. So, let's go through it. Okay, this is C. They live in the same state. So, let's say, is it reflexive? Do I live in the same state as myself? Yes, I do. Does everybody live in the same state as themselves? Yes, and the answer is yes. Symmetric. If I live in the same state as someone else, does he live in the same state as me? Yes. No problem. Okay? Transitive. If X lives in the same state as Y, and Y lives in the same state as Z, does X live in the same state as Z? And the answer is yes, they do. Okay, so it is an equivalence relation. Next, D. P1, P2 for Americans, if they live in the same state, P1, P2, P1, P2, if they live in the same state or neighboring states. Okay, great. Let's do reflexive. Do I live in the same state? Does X live in the same state as or neighboring state as himself? Yes, he lives in the same state as himself. So it's reflexive. If I live if X lives in one state and I live in New York and he lives in New Jersey, okay? So we're in neighboring states, okay? Does that mean that he lives in New Jersey and I live in New York? We're in neighboring states, and yes, it does. So it's symmetric. Is it transitive? Okay? It fails to be transitive. Let me tell you why. Okay? It is not transitive. Why? Because I can live in New York. You can live in New Jersey. New Jersey is connected to Pennsylvania. I don't think New York is connected to Pennsylvania. Okay, so he can be related to him. And he is a neighboring state of him. Okay, this is the bridge between New Jersey and New York. Here's Camden and here's Philadelphia. Okay, anyways, he's related to him, but he is not related to them. New York is not neighboring to Pennsylvania. If it is, I apologize. So it fails. Okay, so it is not an equivalence relation. Okay, P1, P2 for people if P1 have a common parent. Okay, this is number E, common parent. Okay, E. Okay, is it reflexive, symmetric, or transitive? Do I have a common parent with myself? Yes, I do. Everybody has common parents with themselves. Symmetric. If I have a common parent with someone else, does he have a common parent with me? Yes. Okay. Transitive. No, it's not. Let me show you why. Okay. Okay. X could be related to Y because they have a mother in common. Y could be related to Z because they have a father in common. Okay? This person has absolutely no relationship to that person. They don't have anything in common. Okay? So it is not transitive. Okay? Okay? F is have the same mother. Okay? Do I have the same mother as myself? Yes. If I have a sibling with the same mother, do I have the same? Yes. Transitive? Yes. Doesn't have that problem because we're only talking about one of the two parents, namely mothers. Okay, that probably is not a politically correct question anymore, but we're going to ignore that fact. Number 2. For each example of an equivalence relation in exercise 1, describe the members of some equivalence classes. Okay, so we erase so we don't know. So let's go through this. A was an equivalence relation. Those are parallel lines. B was not perpendicular lines. C was the same state. That was. Okay. D was neighboring states. Same or neighboring states. That was not. E was not. And F is. Okay. So, question. What's A? What's a typical equivalence class of A? So A is all those lines parallel to it. So here's a typical equivalence class for A. All these lines. They're all parallel to each other. That's one equivalence class. Here's another equivalence class. Here's another equivalence class. Okay? Don't want to draw too much. Good. So each one of these are an equivalence relation, therefore they have a partition corresponding to it. C. Well, there are 50 states in the United States. Okay? Okay? Every one of them is going to be, here's New York, New Jersey, whatever. Every equivalence class is going to have all those people who live in that equivalence class. Okay? So the equivalence class that corresponds to me is all New Yorkers. I live in New York. Those who live in Delaware, all those Delawareans are going to be there. So that's that. Okay? So you're going to have an equivalence relation. You're going to have 50 different equivalence classes. The partition is going to consist of 50 different equivalence classes because there are 50 states. I'm leaving out Guam and I'm leaving out District of Columbia. It's too complicated. Okay, F. Two parents are the same. So basically, if there's a mother and she has a few children, all those children are going to be the same. Everybody has a mother. Now, some people only have an only child from that mother. So they're going to be their own equivalence class. Okay, so siblings through the mother is going to be an equivalence. Is going to be the partition. An equivalence class is going to be a siblings. Great. Let's look at number 7. Okay, so you're talking about, this is number 7, we're talking about z, positive and negative integers, and we're saying m is equivalent to n in case m squared equals n squared. So let's go through some of them. Okay, 5 squared is 5 is equivalent to, 5 squared is equal to minus 5 squared. So that's 25 and 25. So 5 is equivalent to minus 5. Okay, 7 and minus 7 are going to be equivalent because 7 squared is 49, minus 7 squared is 49. Okay, so first, are they reflexive, symmetric, and transitive? Reflexive, yes, because every m squared is equal to m squared. Okay, by definition. Therefore, m is related to m. Next, if m squared is equal to n squared, does that mean n squared is equal to m squared? Okay, and the answer is yes. Equal has this thing, has this property. Okay, therefore, if m is related to n, then n is related to m. So it works. Okay, same thing for transitive. If m squared is equal to n squared, and n squared is equal to p squared, then m squared is equal to p squared. Okay, what this says is, if m is related to n, and n is related to p, then m is related to p. Can't get more simple than that. So it is reflexive, symmetric, transitive, therefore it's an equivalence relation. Question, what do all the partitions look like? Well, most of the partitions, so here's your z, okay, positive and negative numbers. Most of them look like this, 368, and here's another element, negative 368. 251, negative 251. 7 and negative 7. 3 and negative 3. Most equivalence classes look like that. There's only one equivalence class that doesn't look like that. What does it contain? There's one number that, so most equivalence classes have two elements, a positive and a negative one. There's one element that doesn't. There's one equivalence class that doesn't, and that is 0. 0 is by itself. It's an equivalence class by itself. Why? Because positive 0 and negative 0 is the same number. And 0 squared is equal to 0. Okay, great. Okay, great. Number 9. We're up to number 9. Okay, we have two functions, g and h. They both go from z to n. From z to n. Okay, how are they defined? G of n is equal to the absolute value of n. G of n is equal to the absolute value of n. Next, h of n is equal to h of n is equal to 1 plus minus 1 to the n. Okay, so we have to plug in some things here. So let's do g. G is the easy one. G of 362 equals 362. G of negative 150 is equal to 150. G of 7 is equal to 7. G of minus 7 is equal to 7. Okay, let's do H. Let's do a few examples of H. H of 362 is equal to 1 plus minus 1 to 362. That's an even number, so it's going to be 1 plus minus 1 to the even number, so that's going to be equal to 2. H of 362 with a negative in front of it, I don't even know what that is. I think it's also equal to 2. Okay, H of 3 is equal to 1 plus minus 1 to 3 is 2. H of 4 is going to equal to, nope, that's wrong. 3, that's wrong. Minus 1 to the 3 is 0. 1 plus minus 1 to the third power. Minus 1 to the third power is minus 1. So that's 1 plus minus 1 is 0. H of 4 is equal to 2. H of 5 is equal to 0. H of 6 is equal to 2. H of 7 is equal to 0. Dot, dot, dot. Okay, we see a pattern here. 0, 2, 0, 2, 0, 2. Great. Now let's go through the questions. Now that we understand these functions, describe the sets in the partition of G back arrow of K. Oops. For K is in the codomain of G. What's the possible codomain? Well, every single number is the absolute value of something. Okay? So basically you have a picture like this. Here's Z. I'm going to draw N like an interesting way. Here's N. I should draw it really the other way. Think of this as positive and negative numbers. Here's N. It only has positive numbers. Look, two numbers, 73 and minus 73. Let's draw it like this. 73 and minus 73. They both go to 73. 6 and minus 6 both go to 6. Okay, so what does the partition that this function makes? And the answer is each one has two elements in it. Okay, so here's Z, and each one has two elements, 6 and minus 6. Minus 6. 73 and minus 73. 21 and minus 21. They both go to the same thing. Okay, so that's an interesting way of partitioning Z, positive and negatives. We have one problem, like we had before, 0. 0 is by itself. The only number that goes to 0 is 0. That's it. Okay, that's pretty easy. Next, H is even easier. So here's Z, and here's the natural numbers. And what's the possible output of H? What's the possible output of H? And the answer is there's only two possible outputs, 2 and 0. So we'll call this 0, and we'll call this 2. Great. What goes to 0? What goes to 2? And the answer is, basically, you split it up into two things. Those things that go to 0 are odd. And those things that go to 2 are even. And that's it. So we partitioned it into two things, odd numbers and even numbers. Okay, that takes care of 9. Number 10. So now we're dealing with the natural numbers cross the natural numbers. And we have the following. These pairs of numbers, we have m comma n, and they're related to a k comma l. Okay? And the idea is as follows. If m plus l is equal to n plus k. So if this plus this is equal to this plus this, then they're related. So if m plus l is equal to n plus k. Let's do some examples. 5 and 3 is going to be related to 12 and 10. Let's make sure that's true. 5 plus 10 is 15, is equal to 3 plus 12 is 15. Okay, so these are related to each other. Let's do another one. 374, 215 is going to be related to, holy cow. Let's make it a little easier. 375 to 215. I know the trick, so I can do it quickly. That's 160. So let's see if that works. 375 plus 1 is 376. 215 plus 167 is 376. So they're both 376. Okay, good. Now, we want to show that this is an equivalence relation. Okay, so let's go through it. Is it reflexive? So, question. Is m comma n related to m comma n? And the answer is, well, let's see. Are the outer ones equal to the inner ones? M plus n equal to n plus m. And the answer is yes. Addition is commutative, so yes, it's related. Great. So it's reflexive. Next, is it symmetric? Let's go through that. Okay. If m comma n is related to k comma l. Just before we go further, what does that mean? That means m plus l is equal to n plus k. Question, does that imply that k comma l is related to m comma n? Well, what would that mean? Well, it would mean the same thing. The outer is equal to the inner. Outer, k plus n, is equal to the inner, l plus m. That's exactly the same thing. K plus n is equal to l plus m. Well, if m plus l is equal to n plus k, then m plus l is equal to n plus k. It's the same thing. It all follows from addition being commutative. So yes, it is symmetric. Let's do transitive. Okay. Let's say m comma n is related to k comma l. Okay. Also, k comma l is related to p comma q. Let's see what this would mean. This would mean m plus l is equal to n plus k. This would mean k plus q is equal to l plus p. Great. Okay, great. But what do we want? Let's say this is related to this, and this is related to this. Question, does that mean that m comma n is related to p comma q? Let's see, what do you want here? You want m plus q is equal to, the outer is equal to the inners, n plus p. Let's see. Okay, now, this is a little bit hard. Ready? If this is equal to this, and this is equal to this, so I have two pair of pants, and the same amount of money is in my left pocket as in my right pocket. The same amount of money is in my left pocket, my right pocket, and I combine pockets, okay, adding equal things to equal things. Let's see what that's equal to. So let's do that. M plus L is equal to N plus K. Now let's add that to K plus Q, which is equal to L plus P. I'm adding equal things to equal things. And now I want to know, now I'm going to get equal things to equal things. So now I'm going to get m plus l plus k plus q is equal to n plus k plus l plus p. I added these two things. This is equal to this. This is equal to this. These two things should equal to these two things. That's true. Okay? But look what I want. I want m and q. M and q. N and p. So all I have to do is look at these things, subtract from both sides L plus K. K plus L. Okay, and I get M plus Q is equal to N plus P. Got it. So it's transitive. Great. I'd like to show you another way of looking at this equivalence relation, and it's very, very pretty. So that was the natural numbers cross the natural numbers. I'm going to try to draw some of it. 0, 0. I'm going to leave out the parentheses. 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, dot, dot, dot. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, dot, dot, dot. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, dot, dot, dot. 3, 0, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, dot, dot, dot. 4, 1, 4, 2, 4, 3, 4, 4, 4, oops, messed up. 4, 0, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, dot, dot, dot. Okay, let's see what's related to what. This guy is going to be related to this. 1 plus 1 is equal to 2 plus 2. So this guy is related to this. Okay, and I want to use a different color. 2, 1, and 3, 2 is 2 plus 2 is 4. That's 4. They're related. This is related. These are related. 0 plus 1 is equal to 0 plus 1. Related. 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 Let's just figure out. 0 plus 4 is equal to 3 plus 1. 1 plus 5 is equal to 2 plus 4. Da, da, da. Da, 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 da. Okay. Let me show you what this is. It's actually quite interesting. Okay. What it is the distance between the two numbers. That's what it is. There's one number between 1 and 0. There's one number here. There's one number here. There's one number here. There's three numbers between here. There's 3. 3 minus 0 is 3. 4 minus 1 is 3. Okay, let's do this one. Here it's negative. 0 minus 3 is negative 3. 1 minus 4 is negative 3. 2 minus 5 is negative 3. Da, 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 da. Okay, great. Now let's ask the following question. This basically shows what each equivalence class is. There's Z equivalence classes, because you could have the distance between the first number and the second number could be positive, 0, or negative. So all this is going to be negative numbers. This is going to be 0. These are all positive numbers. Okay, so that's the Okay, so that's an interesting way of thinking about Z. What is Z? It's pairs of numbers. When you subtract them, you get a negative number. So they're pairs of natural numbers. When you subtract one, you get either positive or negative numbers. Okay, number 11. So let's do number 11. Okay, sigma is an alphabet. Oh, so we're going back to what we were doing in the beginning. Alphabet, an alphabet is a bunch of letters, okay? And W1 is related to W2 if and only if the length, length of W1 equals length of W2. Okay, so let's go through it. They want to know, is it reflexive, symmetric, and transitive? Let's go through that. Okay. Explain why it is an equivalence relation. Describe the equivalence classes. Is every word the same length? So Wi is a member of sigma star. Those are words. Is every word the same length as itself? Yes, it is. If you have two words and one word is the same length as the other word, does that mean that the other word is the same length as that? Yes, it is. Is it transitive? If you have two words that are the same length and you have the second word is the same length as the third word, does that mean the first word is the same length as the third word? And the answer is yes, it is. Okay? Words are of finite length. When you say they're equal, and equal means it's transitive. Okay, great. What is all the equivalence classes? Very simple. You're going to have words of length 0. I think we write that like this in this book. You're going to have words of length 1. You're going to have words of length 2. You're going to have words of length 3. You're going to have words of length 4. You're going to have words of length 5. You're going to have words of length 6, etc., etc. By the way, this goes on forever. This is not English where the largest word is 20 letters. This is going to go on forever because it's sigma star. Sigma star is all words of all lengths. Okay, so that was pretty simple. Have a wonderful day.